Hello, it's Mr. Norris, and in this video, we're going to discuss the concept of direct and inverse variation. Direct and inverse variation do an excellent job of explaining real-world phenomena. For example, consider the idea of height, so how tall a person is, and their weight. So let's think about what you would expect in this case. As someone gets taller, what do you think is going to happen to their weight? Well, it seems like as height increases, that weight is also going to increase. And in the same way as weight decreases, we would generally expect height to also decrease. So, that's one example of a relationship that we'll look at with direct and inverse variation. Let's think about some others. I know in the next few days I'm going to be moving to a new apartment, and I'm interested in the time it's going to take me to move, so the time it will take me to move, and the number of people that show up to help me move. So I'm going to put maybe number of helpers, maybe the number of people that are going to show up to help me move. So let's imagine that as the number of helpers increase, what do you think it's going to do to the time it takes to move? Well, the more people I have helping me, the less time it's going to take to move. I could think about that situation in the opposite direction. So the longer it takes me to move, more likely the less helpers I will have. So what we've seen is there's a relationship where as one quantity increases, another quantity increases, or as one quantity decreases, the other quantity decreases. This is a classic example in the height and weight category as direct variation. So this is an example of direct variation. Whereas in this example, the quantity, time to move, decreased as the number of people that came to help increased. So up here we have increasing quantity, increasing quantity. Down here we have decreasing quantity, increasing quantity, such that if one of these quantities goes up, the other is going to go down. This is an example of inverse variation. So we've spoken in general about two real-world examples. Let's try and add some math to this in the next slide. So I'm going to be interested in equations that describe direct variation and inverse variation. So my direct variation formula is going to be y equal to kx. And k is some particular constant. My inverse variation formula is going to be y equal to k over x. So in my direct variation formula, I'm dealing with a case of multiplication. In my inverse variation formula, I'm dealing with a case of division. K is just some number. It's not a variable, we're just using it to describe some number. So k could be 1, or it could be 2, or k could be 5/2. K could be anything. So our task in a lot of the problems that we're going to look at in the coming slides is going to be to determine what that value of k actually is. Let's think about that. Let's do an example problem with direct variation. This says a paycheck varies directly, so that's the first thing I'm going to circle. It's telling me direct variation. So a paycheck varies directly with the number of hours worked. I know that the pay for 20 hours is $238.25. So for 20 hours, I get $238.25. And they want to know what is the pay for 500 hours of work. So for 500 hours, what's going to be the pay for that? Okay, so the first thing that we're going to recognize is that they're talking about direct variation. So I'm going to deal with my direct variation formula, which is y equal to kx. But what does y equal to kx mean in the context of this problem? So I recognize that paycheck is coming before the word directly in the question that I'm given. As a strategy, most often, the item that they're talking about before the word directly or inversely most commonly refers to your dependent variable, to your y. So I know that y is going to refer to my paycheck, so maybe I'll put p in for that. Okay? I don't know what k is, so I'm still trying to figure that out. So as I'm reading through here, it's talking about paycheck varies directly with the number of hours. It looks like number of hours is my x. And I'm basing that upon that general strategy that typically when they're talking about your independent variable, your x, they're talking about whatever quantity comes after the word directly. So let me consider my number of hours. And I'm going to put in for number of hours maybe n. So I have now that my pay is equal to k times the number of hours that I work. So we really need to deal with these problems in 2 steps. So first, let's think about the first step. So our first task is going to be to find k. The problem's telling me that when I've worked for 20 hours, I've made $238.25. So I'm going to substitute in $238.25 for p. So now I have $238.25. And I'm going to go ahead and set that equal to kn. So equal to k. N, I know that when I have $235, I've worked 20 hours, so I'm going to put in 20 in the place of the letter n. Okay, now I have this, and I can just do some algebra to solve for k. So I'm going to divide both sides by 20. Alright, and I'm going to get out that k is equal to 238.25 over 20, which that's going to be $11.91. So this k I call my constant of variation. And it means different things depending upon the real world context that you're referring to. In this case, my constant of variation k means the hourly rate that I get paid. I get $11.91 an hour based upon the fact that when I had worked 20 hours, I had made $238.25. So now I have an equation relating the money that I make and the number of hours that I work. And that's going to be P equal to $11.91 times the number of hours that I work in. But I might feel like I'm done right now, but I actually have a little bit more work to do, not too much. The real question is, what is the pay for 500 hours of work? So my first step was to find k and get this function. But now I need to find out the answer to the specific question that was being asked. So this is going to be my second step. So they're asking for 500 hours. I'm going to do P equal to 1191. And instead of putting in, I'm going to put in 500. So now I have 1191 times 500. And I get out about $5,955. Alright, so this is our first example of taking a real world problem and trying to create a direct variation formula for that problem. In our next example, we're going to look at inverse variation. In this example, the amount of time it takes to get to campus varies inversely as your driving speed. So I know that I'm thinking about inverse variation, so I need to write out my formula for that, y equals k over x. And I know that the amount of time came before the phrase varies inversely. So strategically, I'm going to think that the amount of time goes in the place of my y value, and driving speed came after the phrase varies inversely, so I'm thinking that driving speed most likely goes in the place of this x. So what I'm really relating here is time, and that's going to be equal to some k over my driving speed. Maybe I'll call that s. So I'm going to do k over s. Okay, let's keep reading. It's telling me you're in bad traffic and drive 20 miles an hour, and it takes 1.5 hours to get to campus. So if I'm going 20 miles an hour, it takes about an hour and a half to get to campus. So using that information, let's see if we can figure out the constant k. So I drive for 1.5 hours, And I don't know my value of k yet. I don't know my constant of variation. But I know that my speed is 20 miles per hour. So at this point, I'm going to try and solve this for k. So I'll multiply both sides by 20 over 1. That'll cancel out. Multiply this side by 20 over 1. And then we'll get k equal to 20 times 1.5. And 20 times 1.5 gets us to 30. So now I know that k is equal to 30. So this was my first step where I found k. And now I have my new equation relating time and the speed that I drive. So that time is going to be equal to 30 over the speed that I drive. So now it's asking me, how long would the trip have taken if you drove 50 miles per hour? So now in the second part, I'm simply going to use this equation. So they want to know time, and they're giving me speed. So I want to know time, and they're giving me that I drove 50 miles an hour. So I put 50 in for S, and I get that time equals 30 over 50, which is equal to 3 over 5. But what does that mean, that time equals 3 over 5? It's uncommon that if somebody asks you how long it's going to take for you to get to a restaurant or how long it's going to take for you to walk from one place to another, that you tell them 3 over 5. Consider your units. You're talking about hours here. So time is referring to 3/5 of an hour. So if we want to think about converting this, time is 3/5, but we're talking about 60 minutes in 1 hour. So 3/5 times 60 gets us to 36 minutes. So just an additional note there in blue at the bottom left right hand corner of your screen. Just to note units and consider that sometimes you may get an answer that may not make complete sense until you start thinking about the units that you're working in. So this whole process wasn't very different from working with direct variation. It's simply a matter of considering the equation that you're given and going from there to find the constant of variation and then substituting in some value to answer the question that you're given. So two-part process. So far you've thought about direct variation, thinking about y equals k times x, and you've also thought about inverse variation, where you're thinking about y equals k over x. But there are special forms of direct and inverse variation called power models. So in both of these examples, y equals kx and y equals k over x, your x is raised to the first power. And we don't even include that to the first power because if there's nothing there, we just assume it to be true. Okay? So we don't even think about these two. But in reality, you can raise that power to any positive integer. So let's think about that. Let's consider some other examples where maybe I could take y equals k times x squared, or maybe I want to think about y equals k times x cubed, or maybe I want to think about y equals k times x to the some integer n. And we can do the same thing with inverse variation. Maybe I want to think about y equals k over x squared. I want to think about y equals k over x cubed. Or y equals k over x to any integer n, to any positive integer n that I want. So when you're looking at these types of direct variation and inverse variation, we're talking about power models, situations where we take the direct variation formula and raise this x to some power other than 1. These are less common in real-world situations, but they're still interesting to consider. Let's look at some examples. Okay, so let's work through an example of a power model with direct variation. So it says that r varies directly as the cube of s. So I'm going to write my direct variation formula. R comes first before directly, so I'm going to put r equal to k, since I'm working with direct variation. And it says as the cube of s. So instead of just putting s, I'm going to put s to the third power. So this takes the general form of y equal to k to the x, but since it's a power model, I'm talking about the cube, I'm raising that to the third power. Okay? They're telling me that r equals 5 when s equals 3. So I'm going to put in 5 here for my r, and I'm also going to put in 3 for my s. So I have r equals 5 equals k times 3 to the third power. So now I have 5 equal to k. 3 to the third power is 27. Then I divide both sides by 27. And I get out that k is equal to 5 over 27. Alright, so I'm going to take that value of k and put it back into my original formula. So now I'm going to have r equal to 5 over 27 times s to the third power. Now time to answer my original question. It says find r when s is equal to 2. So find r when s is equal to 2. So I have this formula now that I can use. They're telling me that s is equal to 2. So I'm going to go in here and I'm going to solve it. I'm going to find r. So I'm going to write r equal to 5 over 27 times s. And s is 2, so I'm going to put in a 2 here. Raised to the third power. I'm going to rewrite this now that I know that I have 5 over 27 times 2 to the third. 2 to the third is 8, so I'm going to do times 8. Now, I recognize that 8 times 5 is going to be 40, so now I have r equal to 40 over 27. So at this point, I've answered my question. I found that when s is 2, I know that r is equal to 40 over 27. So I really go through the same process that I did with the previous two examples. I write my direct or inverse variation formula. I find my constant of variation k. Then in my second step, I try and find what the value of r is. So in that first step, I'm considering writing the formula and using the information that I'm given to find the constant of variation. And in that second step, I'm answering the actual question. I'm finding r when s is equal to 2. Let's look at one more example of a power model. But since we did direct variation in this case, let's consider inverse variation in the next one. So let's try and solve this problem. The first thing they're telling me is let y vary inversely with the square of x. So I'm going to go ahead and write that out. Y is varying inversely with the square of x. So I'm going to think about my inverse variation formula, but instead of just doing k over x, I'm going to do k over x squared, since we're talking about inverse variation with the square of x. Now they're telling me I know x equals 8 when y equals 2. X equals 8 when y equals 2. So they're giving me all the information I need here to solve for this value of k. So let's go ahead and sub that in. We know that y equals 2 when x equals 8. So I'm going to put k over 8 squared. Okay? And this is going to turn out to 2 equal to k over 8 squared, which is 64. Now we'll just multiply both sides by 64. So now we're going to put that over 1. We're going to do the same thing to the other side. We're going to multiply it by 64 over 1. Those two 64s cancel. And we get k equal to 2 times 64 over 1, which we can just write as 64. And 64 times 2 is just equal to 128. So now we have k equal to 128, which is precisely what we wanted to find. Now we have a much better situation where we have an actual equation. Y equals 128 over x squared. So they're asking me to find x when y is 16. Okay, let me go ahead and substitute in 16 for my y. So I'm going to put in 16 equal to 128 over x squared. Okay, I'm going to multiply both sides by x squared. Oops, meant to put that over 1. I'm going to do the same thing over here, x squared over 1. And I'm going to get out 16 x squared equal to 128. Okay, I'm going to divide both sides by 16 now. 16 goes into 128 8 times, so now I have x squared is equal to 8. And then I can just take the square root of both sides. And I will get, that's an interesting square root sign I drew, then we're going to get x equal to positive or negative square root of 8. It's perfectly fine to leave your answer in square root form. Okay, so again, we did that same process where first we had to find the constant of variation, and then we had to answer the actual question. This question is a little bit different than previous questions in that in previous questions, when you had to do this second step, typically they would give you an x, and then you would find a y. But this time, I gave you the y, I told you that y was 16, and I asked you to find the x. It's a little bit more complicated, but it's still possible to solve for this value of x, because we did it. Okay, that's going to conclude this video. We've discussed direct and inverse variation, specifically how to find the constant of variation and answer questions when it comes to actually obtaining that equation. And we've also discussed power models, situations where in our direct and indirect variation formulas, we have x raised to some power other than 1.